Now more than ever, innovative technologies are fueling change and sparking new ways of thinking. Collaboration between corporations and startups is key to staying at the forefront of these trends. However, finding the right startups can be expensive, time-consuming, and ineffective. But Plug and Play is here to help. As a corporate partner, you will gain access to a whole ecosystem of innovation. Discover startups that meet your tech interests. Stay updated on the latest trends and network with industry peers. We will help you during every stage of your innovation journey, no matter where you are and where you want to go. Get in touch today.
Hello, everyone. My name is Salman Jar, and I'm a corporate partnerships manager here at Plug and Play. I'm very excited to speak with you all today, and thank you for joining the event. So, Plug and Play, at least what the market is referring to us, is the largest global innovation platform. And we have 3 pillars here. Our first one is we run accelerator programs in different cities. The second is that we work with 500 corporate partners to fuel their external innovation strategies. And the third, we invest. As Plug and Play, we deploy capital to 200 to 300 startups every year. So we run accelerator programs, we work with corporates, and we invest. Our mission as a company is to really drive innovation by connecting all the players in the ecosystem, from entrepreneurs, corporates, governments, universities, and investors. And for this to be true, we feel like innovation needs to be open to anyone, anywhere. We have a really interesting history dating back to the early 1990s, where our founder and CEO, Saeed Amidi, was able to house, invest, and accelerate some of the best companies that Silicon Valley has ever produced. Companies like Google, Logitech, and PayPal. And it was here where this model of investing in startups and providing resources really began, right in the heart of Silicon Valley on University Avenue, where we're fortunate enough to house companies like Google and PayPal. We also have the good fortune of investing in these companies, and that is where we decided to take this model and bring it to scale. Today, we have over 38 offices around the world, and what we've tried to build is this connected network of innovation platforms, which allow startups access to new markets and corporate partners that we work with, visibility to places they do not have boots on the ground. So you can imagine a startup that just raised a Series A in Silicon Valley and is looking to tap into the Europe market, can have a soft landing in Vienna, Stuttgart, Geneva, or Paris, and vice versa. A company that's looking to raise a Series A that's based in Europe can come to Silicon Valley and have access to all the corporate partners and venture capitalists that we work with here in the Bay Area. We have about 1,700 portfolio companies, of which 1% have exceeded $1 billion in valuation. Companies like Honey, Dropbox, Lending Club, SoundHound, Hippo, and PayPal. We also have about 10% of our portfolio that exceed $100 million in valuation. So we've had a very great track record. Part of the reason we have had so much success with our investments really ties back to our corporate partnership model. We soon realized investing money into startups is great. Giving them money to start companies, obviously very important, but oftentimes even more valuable is introducing them to customers that can actually validate their technology in the market with the large companies, say McDonald's, Coca-Cola, Adidas, Microsoft, or Yum Brands. That could be a game changer for a new startup. So what we've done over the years, we've partnered with almost 500 companies across every other industry that are actively coming to us to meet new startups that are aligned with specific business challenges that they're looking to solve. And so we provide access to our corporate partners in a variety of ways, but our main way is through something we called our themed innovation platforms that are industry-specific accelerator programs, where we bring together multiple corporations that represent a specific industry to collectively dictate the focus of the program, collectively filter the application that we receive organically and proactively, and then jointly select the startups that make it into a 12-week program. So we do this twice a year per vertical in Silicon Valley. That's 18 verticals here. So that's 36 accelerators throughout the year. And then you scale that out to 37 locations. So we're working with and seeing a lot of startups. I'd like to conclude the overview and opening remarks. I'd like to introduce Mickey and Ken.
Hi, thank you, Sol, for the introduction. And thank you, everybody, for coming to join this webinar today. We're excited to be here to share exciting experiments that's happening in International Space Station, and also joined by our colleague from Australia, Cyro, to share their view on carbon capture and the opportunity for partnership. So my name is Miki Sode. I am a Commercial Innovation Manager at Center for the Advancement of Science in Space, the manager of International Space Station US National Lab, and joined by Ken Savin. He would introduce himself in the second half of this presentation. So let's start off by brief history of the International Space Station and ISS National Lab. So the construction of International Space Station started in 1998. The first US-built component was launched and with the space shuttle. It was the first one dedicated just for the assembly of the space station. ISS took about 10 years and more than 30 shuttle missions to assemble. It's the result of unprecedented scientific and engineering collaboration, as well as international collaboration among 5 space agencies. So, of course, NASA, European Space Agency, Japanese Space Agency, Canadian Space Agency, and Roscosmos, and all in all representing about 15 countries. And in November 2000 is when 3 astronauts started habitating International Space Station. And since then, continuously. So last year, we just celebrated 20 years of continuous human presence in space on board ISS. Some fun facts about ISS it's about the size is approximately the size of the football field. Interior living space is about the size of a 5-bedroom house. It travels around Earth at the speed of 17,500 miles per hour. So that means they orbit the Earth every 90 minutes at the altitude of approximately 250 miles. That means astronauts experience 16 sunsets and sunrises a day. So far, over 3,000 experiments from 190 plus countries conducted on ISS, and that's, of course, counting up. 240, and again, more people now, individuals from 19 countries have visited ISS so far. So in 2005, US Congress designated US portion of the ISS to be the national lab. And then most of the national lab out there, like the Lawrence Livermore or Sandia or Brookhaven, they are DOE, Department of Energy national labs, but we are national lab of NASA. But the premise is the same. The government wanted to open it up to maximize its use by the non-NASA US government agency or academic institutions, private sectors, to leverage this unique environment and facility on board the ISS to advance science, technology development, and education to ultimately improve quality of our life here on Earth and promote collaboration. So in 2011, Center for the Advancement of Science in Space, or CASIS, were selected by NASA manage this the national lab portion of the International Space Station. So we strive to foster scientific discovery and technology innovation in space to expand US leadership in innovation and in commercial space sector, and of course to inspire the next generation through ISS STEM education opportunities. So how do we accomplish that? We manage the International Space Station National Lab as a public service in order to benefit the US taxpayers to foster scalable and sustainable low Earth orbit economy. We leverage our core competencies, facilitate public-private partnership, utilize the platform capabilities and unique operating environment of the space station. And we create demand, incubate in space business ventures, provide access for and awareness of fundamental science and technology innovation, and promote science literacy for the future workers. So why space? Essentially, research in space provides a paradigm shift. It reveals features of terrestrial life and physical processes that cannot be seen or manipulated here on Earth. So space and the ISS provides a platform to study more about microgravity environment or extreme conditions and vantage point. Microgravity or weightlessness alters many observable phenomena within the physical and life sciences. So systems and processes that are affected by microgravity include surface tensions or surface wetting and interfacial tensions, heat transfer, fire and combustion, to begin with. And on the life science side, microgravity induces a vast array of changes in organisms ranging from viruses to bacteria to humans and plants, including global alteration in gene expression and three-dimensional aggregation of cells into tissue-like architecture. The ISS also provides access to extreme
Sandy
conditions.
and Pam in the ground, like you have real support.
I didn't know that there's a sound for it, but yeah. So exposure to extreme heat and cold cycling, alter vacuum, atomic oxygen, and high energy radiation. So testing and qualification of materials or sensors or subcomponents in this extreme condition have provided data to enable manufacturing of long life, reliable components to use on Earth and in space as well. And the last but not least, the ISS offers a unique vantage point based on its location with low Earth orbit. So the ISS offers a unique vantage point that the other, say, sun-synchronous or geosynchronous satellites cannot do. The vantage point from the altitude of 250 miles, and its orbital path covers more than 85% of Earth's surface and 95% of world's populated area. So these data could be used for monitoring atmospheric activities in agriculture and storm tracking. All in all, ISS is a orbiting lab. And so we have freezers, furnaces, centrifuge, microscopes, cell cultures, incubators, and the list goes on and on and on. And then ISS National Lab offers diverse state-of-the-art hardware like these. And we facilitate to support a wide range of variety of research equipment that's provided by our implementation partner and service providers, so that would enable the R&D effort and technology demonstration on ISS. And also the ISS are crewed. So these men and women up there right now are carrying out your research every day. Many astronauts out there are trained scientists, from microbiologists to plant scientists, so that they have deeper understanding of what's important for your science. But why do we do all this? Ultimately, our goal is to enable space research that leverages these unique conditions so that result can be used to improve our lives here on Earth. So ISS National Lab CASIS strives to bring value and impact back to the US taxpayer and economy by benefiting life here on Earth, from new drug development to new materials development, or hyperspectral sensors to monitor environment, or new optical fiber materials with superior quality. So the ISS National Lab enables science in space to benefit life on Earth. Before I pass the mic to Ken, I want to quickly go over our portfolio. So you will see our project it spans a wide range of disciplines such as life sciences, physical sciences, remote sensing, technology development, and partners that you may have heard of, but don't necessarily associate with space. So as you can see on the pie chart over there, the large percent of our portfolio is in life sciences, about 43%. We have good balance between commercial and academic nonprofit representative, as you could see in those bar graphs up there. And 72% of new projects are from new to space investigators, including large multinational companies like Bristol Myers Squibb or GlaxoSmithKline and Adidas, Delta Faucet, Goodyear, Merck, those companies that you heard of but not necessarily associate with space. And we have some returning customers as well. So National Cancer Institute and Hewlett-Packard Enterprise, they just send a spaceborne computer to an International Space Station. And they seek to build on past R&D success and onboard to build on with the more additional experiments on the ISS. So with that, I will like to bring Ken to present and talk about CO2 effort that we have on ISS.
Hi, everyone. My name is Ken Savin. I'm a chemist by training. I was originally a principal investigator with the National Lab, worked for the pharmaceutical industry, worked in the pharmaceutical industry, and left pharma and got hired on by the group at the Center for the Advancement of Science and Space. So I'm going to right now take a few minutes and kind of lead us into a discussion around CO2 capture and utilization, and then that will lead into the next presentation. I'm going to start with this right here. This is the famous mailbox, the on-the-fly built CO2 puller that was put together from pieces and parts on the ill-fated, but fortunately not tragic, Apollo 13 mission. And it's a good example of what it takes to pull CO2 out of the atmosphere and kind of the need to do so just for the sake of our lives. And what I've shown down there, and I'm not expecting anybody to have flashbacks to their general chemistry class, but it's a pretty simple process. You build a device that will blow the atmosphere through a cartridge that is filled with something like lithium hydroxide, which I've shown down below, and CO2 mixes with lithium hydroxide to form lithium carbonate, which is a solid and is stuck in there, and water. As the process continues, not only are you sucking up all the lithium hydroxide and pulling the CO2 out, but the lithium carbonate is formed, and then the water gets it moist, and after a while the cartridge doesn't function anymore and you need to replace it. And it's not reusable. You essentially make it and then you dispose of that cartridge. And for short missions and for certain situations, it is a spectacular solution. It works really well and has seen a lot of utility over time. But for longer term missions, and as an analogy to our situation of looking at carbon capture for the benefit of people on Earth, you've got to find something better. And there is a better solution. If we look at the overall life support system for the International Space Station, this is how NASA looks at it. Now, I don't want you, there's a lot going on here. I don't want you to spend a whole lot of time on all the bubbles, but look at the yellow bubbles and the purple bubbles over on the right. Those are really the ones that we're going to focus on. The yellow bubbles show trace contaminants, which might be particles, dust, or debris that's in the air that gets filtered out, and then CO2 removal. And in the past, just as I've shown, CO2 is essentially overboarded, is what they would call it, or thrown away, but they would capture it in a cartridge and dispose of the cartridge. That's the old way. Down in the purple bubbles, they show where they're making oxygen. So you can only bring up so much oxygen, but if you had a way to make it on station, that would be spectacular. And they do have a way, and I'll show you that at the end of my little presentation. But they also were generating hydrogen, and that was also considered a waste product, which was overboarded. And there is a process by which you can take those two waste products and make something of use. And I show that in subsequent slides. The Sabatier process is the solution to the problem of capturing CO2 and then generating something of use from it. So you don't have to dispose of everything. The process takes CO2, mixes it with hydrogen, and that is pushed, blown over a hot metal catalyst that's heated to about 300-400 degrees, and the product is methane, CH4, and water. And you see the delta H is minus 165 kilojoules per mole. That means that it's actually giving off energy. It generates energy in this chemical process, and it gives it off in the form of heat. There's a couple of interesting things to say about this process. The first is, because it generates heat, it's got a negative delta H, it actually is a self-propelling process. Once you start running the process, the catalyst gets hot on its own. You don't have to heat it anymore because it's an exothermic process giving off heat. And as long as you supply it with more CO2 and hydrogen, the reaction will occur. So it's actually a really great sort of downhill process. That's the first piece that I think is really interesting. The second is, if you're going somewhere where you need to make water, for example, let's say Mars, if you have plenty of CO2 and the Martian atmosphere is carbon dioxide to CO2, then you've already got one of your starting materials there. Problem, though, you run into is that you need hydrogen. And even though hydrogen is the most common element in the universe, it is not always available to us in the form we need it. Hydrogen in the form of gas that is released into our atmosphere leaves our planet. It floats up above the atmosphere and out into space. And so the only hydrogen we have is stuck in materials, organic materials like trees and people, chemicals that are found in the ground and what have you. And as a friend of mine, Lane Carter, a NASA engineer, said to me, all I want are my hydrogens back. He just wants to get hydrogen so that he can do things with it. For example, run his Sabatier process. So, so we've got to find a way to get there. Now, there's one last unique thing I want to say about the Sabatier process. And here on this slide, I have a picture of Paul Sabatier and a little note down here that is the description of what his accomplishment was. It says, for his method and of hydrogenating organic compounds in the presence of finely divided metals, Paul Sabatier received the 1912 Nobel Prize for Chemistry. So the key piece here is, although this guy was a total genius, we are dependent upon science, chemistry, that was developed over 100 years ago. That is how old this process is, even older than that, since he was working on this in the late 1800s. So we've got to be able to do better. And we'll talk about that. Well, Erin's going to talk about that, some of the improvements. But it is fascinating, I think, to see that an old process that is so totally reliable is still something that we rely upon because the technology was so good. And in some ways, we have had trouble pushing beyond it. But there are some solutions to get us beyond that. Now, before I leave this whole topic, there's a few more things I wanted to say. I talked about the CO2 removal. Those were in the yellow buckets. That's the Sabatier process. But down below, I want to say just a few words about oxygen generation and how that also works into this overall cycle. I've shown here a cell for generating oxygen gas. This is the process that is used on space station for generating oxygen. And it was developed and sort of proven during the development of the nuclear submarine program in the United States. And it's a pretty common type of technology. So it's a cell that is filled with water, and the two halves of the cell, the anode and the cathode, are separated by a membrane or a bridge that only allows electrons to pass, but not chemical materials. As I've shown on the cathode side on the left, hydrogen is generated. Water is, to water is added electrons, and that's a charge, or you're putting electricity through it, and you're generating hydroxide and hydrogen gas. And the hydrogen gas is captured and then applied in the Sabatier process I mentioned. In the other cell, you're removing electrons. This is the anode side, and you're generating oxygen and protons, and electrons are removed. The process is separate because you don't want the oxygen and the hydrogen mixing. You want them separate. You won't be able to capture them separately. They're explosive in mixture when they're together. And you can see the net reaction down at the bottom. Water is converted into oxygen and hydrogen through this process with a delta H that is positive 237.1 kilojoules per mole. That means that you actually have to pump a lot of energy into it to get it to work. So with that in mind, we are able to generate not only oxygen, but we're generating the hydrogen we need as well. So through those two processes, the Sabatier process and the this electrochemical cell, we're able to generate the materials to remove CO2 and to generate water, which then can be put into this process. And again, we make more hydrogen and oxygen. What I've tried to do is show how the life support system works, because it's a good analogy for our own situation here on Earth, where we're trying to use things that have already been produced, perhaps as waste products, and recycle them for use in other ways. And just as, for example, trees are pulling CO2 out of the atmosphere to then ultimately generate oxygen for us, the environmental control and life support system on station is doing the same, but through more chemical means. But through all that, it leads us down the path of what can we do to improve our situation by pulling CO2 out and not just sequestering it, but actually using it to produce things that are of use to us. And with that, I'm going to sort of close out, and we'll then turn it over to Aaron. If you do have any questions, you can contact us at the International Space Station, U.S. National Lab. There's our link right there. And I know that Mickey and I would be happy to answer any questions. You can also contact us outside this webinar as well.
Hi everyone, my name's Aaron. I'm calling in today from Down Under. I'd like to thank the organisers at Plug and Play for organising the event. And I'd like to thank Mickey and Ken for the invitation. Today I'll be talking on carbon dioxide recycling. This work is done at Australia's National Science Agency called CSIRO. Our team focuses on the discovery, manufacture and application of porous materials. And here's a nice microscope image of the crystals that we've been growing here that are highly selective for carbon dioxide. Now, space research has always pushed the boundaries of what we can do. In terms of controlled atmosphere, if we would like to travel in outer space, like one of the first Apollo missions here, we have a person who breathes about a kilogram of carbon dioxide each day at roughly 4% concentration. So fairly quickly, if you don't remove that carbon dioxide, you will suffocate. So controlling the atmosphere making sure it's breathable, and then reusing any of those components that you capture is critical for long-term missions. Now, back on Earth, we're now seeing how thin and vulnerable our own atmosphere is. We have issues like global warming and pollution, and so we'd like to apply similar technologies to control our carbon dioxide and our heat and humidity on our own planet, and create a closed loop of all of the molecules that we have on our own planet. A bit of history on CO2 scrubbing in space. So in fact, the first missions just took up compressed air like you would for scuba diving. You have these little spherical gas vessels here, and you would just replenish the air as you went. And you can imagine that you're limited really to how much air that you can take up there. We then moved on to a material that can remove carbon dioxide. So this is lithium hydroxide or LiO. So as you breathe, it would strip out the carbon dioxide so you can continue to breathe that atmosphere. So that would extend our survival up there in space. Problem with this technology though is you can't regenerate it. So as soon as the canister's full, you either have to reuse a canister or send up new canisters. So we moved to a regenerable system. So zeolites have been up there for decades now, starting with the first space station, so Mir and Skylab, and now the ISS. And we call this a 4-bed molecular sieve system. So this is great. It can capture the CO2 and then regenerate the material. In fact, we're also reusing the component of oxygen out of that carbon dioxide. So recently, 2010 or 9, they introduced a Sabatier reactor to recover the oxygen. And so what's left now is methane or the waste product from this process. So we're actually releasing carbon and hydrogen, which still are very useful molecules that we need to recycle. Now, we did a scoping study here at CSIRO. We looked at all of the supplies that are being currently provided to the space station, and we were seeing whether you can use carbon dioxide or methane, so the carbon, oxygen, and hydrogen, to manufacture any of these supplies on board, especially as we move to the moon and Mars. Now, rough categories are medicines, vitamins, food, fuels, and materials. And I've just put a few examples here. So ibuprofen, and so a bunch of medicines and a few vitamins were shown to degrade at a faster rate in space. So these are even more important that we manufacture those in space rather than relying on deliveries from Earth because of their lifetime, even when they reach space. So you can see here the chemical composition, so carbon, hydrogen, oxygen. And this this applies also to glucose, so sugars in foods, and then propellant, so the simplest being methane itself, but other propellants as well. And then finally, materials. So 3D printing has become a popular way to manufacture at the time that you need the equipment. And in fact, this low density polyethylene here is a common material used in 3D printing that could be manufactured as well from our current waste products. And then back on Earth, so our carbon dioxide levels are going up. We dump about 35 billion tons per year. And in fact, our current CO2 market is 100 million tons. So there's already a direct opportunity to start to remove that carbon dioxide from the air and distribute internally. That does not include any renewable fuels, which I'll talk about a bit later. Now, we took this video in our lab, so we've filled up 2 balloons with carbon dioxide, and then we've placed a tiny amount of our new sorbent, called a metal organic framework, down here in the vial. Now you can see that the tiny amount of material has absorbed all of that carbon dioxide. This was very exciting to see that it works, and that we could in fact remove so much carbon dioxide given a tiny amount of material. And a rough calculation indicates that if we made a kilogram of that material, then we could remove as much as CO2 as 20 trees would in a year. Now, metal organic frameworks are actually invented down here in Australia in University of Melbourne by Richard Robson back in the 90s. And so these were really exciting materials. They're crystals, and so they self-assemble. They're composed of a metal ion or cluster as a cornice, and then linked by organic linker groups. So the organic part is what you'd find in plastics or polymers, but instead of a long chain, you've just got these tiny chains. And then, well, metals we're familiar with. But the structure that we get out is kind of like a zeolite. So it combines materials of metals, polymers, and zeolites. Now, if you looked at all of the possible combinations of metals out there, as well as organic linker groups, there's over 1 million different metal organic frameworks theoretically that you could make. And in fact, across the world, I think we're close to 50,000 different frameworks that have been made. So there's a huge range of chemical tunability as well as the pore sizes for these materials. And then what we've focused on for carbon dioxide is getting the right pore size and the right chemistry to selectively capture that carbon dioxide. So we want to capture the carbon dioxide, which is a small amount, usually in the air, so 0.04% here on Earth. But also you want the energy requirements to kick that carbon dioxide out low too, so you can continue to regenerate the material without requiring much energy. So compared to all the other materials here, we find that MOFs have more sites, so you can fit more carbon dioxide given a certain amount of material, and also you need less energy to remove that carbon dioxide, mainly because we're not capturing carbon dioxide chemically. It's physically trapped in these pores using van der Waals forces as well as electrostatic forces. So this is how it differs from amine-based materials, solids and liquids. It's similar to zeolites, but in fact, our material, so for zeolites, you need to dehydrate the air because water competes with carbon dioxide for the sites. But because MOFs are so chemically tunable, we've been able to tune that so that water passes straight through and does not compete for those carbon dioxide sites. And then finally, compared to the LiO system, lithium hydroxide, it is regenerable. And so you can continue to capture and release. So we went and manufactured about 10 kilograms of our adsorbent, and what we did is we made a thin film technology that we call a nanocomposite film technology. So we coated these long, flexible heaters, and then we scrolled up these heaters and placed them in modules. And so the air basically passes through the module, the sorbent captures the carbon dioxide, and then when the thin film has captured as much carbon dioxide as it can, we use heat and vacuum to release. So we went ahead and built 9 modules and connected them all up and automated this unit. We call the whole technology Airthena, and this unit could capture about 2 tons of carbon dioxide per year, which is equivalent to support about 6 astronauts in space. And we published just recently last year in Advanced Sustainable Systems, and we reported the lowest energy consumption to capture carbon dioxide, which is about 2.3 kilowatt hours per kilogram. We also submitted a few patents. And then what we're doing now, so you can either scale up the technology or scale down the technology. We're looking at redesigning a unit for the lunar habitat. And also we're looking at scaling up the technology. So we're building a second unit, which is 100 tons per year to demonstrate proper capture and utilize carbon capture and utilization here on Earth. And then finally, I'll end with a bunch of markets that you could use this technology for. So we found greenhouses and even more recently, algae farms use a lot of carbon dioxide to accelerate the growth of food. So that industry is at about $14 billion. Then there's dry ice at $40 billion for cooling and cleaning. We've seen a spike in dry ice for the vaccine production that requires cooler temperatures during transport. Then there's beverage, so carbonated beverages, beers and soda waters and soft drinks, so at $12 billion. Then there's a new market. There's a few companies that are using carbon dioxide to make concrete. I wasn't sure about the market value there, but concrete and cement are the most man-made substance in the world. So you imagine that industry being rather enormous. Then there's a fun one, a home soda. So those who use SodaStream or the like, instead of replacing your cylinders, you may be able to produce carbon dioxide at home directly from the air. And then finally, which is probably the biggest, is if we can convert that carbon dioxide back into fuels, so methane or ethanol, that industry is up towards $600 billion. And that's a very nice one for climate mitigation, climate change mitigation, because we genuinely have a closed loop there where we can continue to use fuels as long as we capture that carbon dioxide that's emitted and reuse it, and also make sure that we use renewables when we're doing that. So I'll just finish with acknowledging some funding resources. So we had two funding sources, our Science and Industry Endowment Fund and also our space program in CSIRO. And I'd like to thank quite a lot of the team involved to get the technology this far. And thank you for your attention, and I hope you enjoy the rest of the event.
Hello, everyone. Thank you, everyone, for speaking. And now we're going to enter our Q&A. But before we do that, I'd like to introduce Julia.
Hi there, everybody. My name is Julie Noblet. I'm the...
Julia.
That's okay. I go by Julia, too. I answer to both. I am the Director of Strategic Partnerships in the CSIRO US office. And since we got to hear the presentation by Aaron Thornton on Athena, but he couldn't join us live for time difference reasons, I am here to let you know that if you have questions, I am the person who can get them to Aaron, and I am also the person who can set you up if you would like to have a meeting and learn more about how this Athena technology might apply in your particular situation. So CSIRO, I'll just mention quickly, is Australia's National Science Research Lab, and we focus on solving global problems like this one, CO2 capture, but many other things. And we focus on commercialization. We have hundreds of licensable patents. So that's all I'll say about that. Thank you so much for joining. And again, for technical questions, I can pass those on to the scientist, and otherwise I'm here to connect you.
Awesome. Thank you for the intro, Julie. Yeah, so I guess we'll get started. Question that I have is, I guess we'll start off with CASIS and then we'll go with CSIRO. So first question is, how can everyone from our plug and play corporate partners work with CASIS? Mickey or Ken, feel free to add in on this.
Yeah, so we, CASIS, we work with startups as well as Fortune 500 companies. And we also work with accelerators like Plug and Play or a Mass Challenge in Boston. And that's how we connect. I think it's a direct connection there. But like when we work with startups, we basically help them reach the higher potential in a way by just giving an access to this orbiting lab so that they could advance their science discovery or do a technical demonstration, mature the technical readiness level, right? So that you can go to market faster. And then they also get that leverage to raise more capital as well. But as for the corporations, say, for example, we've worked with one of the Plug and Play community member, Procter & Gamble, for product innovation, and so that they could provide more, say, it could be sustainable materials or superior quality product to the consumers as well. And maybe Ken can speak more about this, but not only we do a basic R&D effort that will be done in space, but that can only be that could only be done in space, but also its application is for here on Earth as well as in space. And the value that we provide by doing those scientific discovery and technology demonstration is short term as well as long term. So, and then I think we could look at that as a holistic viewpoint and different ways to collaborate with CASIS.
Awesome. Thank you, Mickey. And then same question to you, Julie. How can our Plug and Play corporate partners possibly work with CSIRO?
Yes, great question. There's several ways. So as I mentioned before, CSIRO has hundreds of licensable technologies. So I'd say if you're a corporation with a problem that needs solving, a technical scientific problem that needs solving, you can reach out to us here in at CSIRO here in the US. That would be me, but we have offices also in France and in Chile, and talk to us about solutions that we might have to offer. We also look for corporate partners in terms of investing in new technologies, in pressure testing them. So if you have an investment arm, a future technologies arm, and you are looking for partners, we'd be a source for that. And I'd say for startups too, if you've got a great idea and need help with the technology, reach out to us. There are, we, as I said, have hundreds of technologies that might actually suit your need.
Awesome. So I think we're starting to get some questions popping up in our Q&A. So yeah, so we have a question from Bar Stoltz. He says, we also have a very similar solution, but more advanced compared to the presented ones. Are you open to direct cooperation? I hope I said that correctly. I think this is just a general statement. Okay, well, we have another question. Is the MOF is refused over and over where the CO2 goes after? Is it first captured since it's physically, there's no reaction in a limited amount of space? So I guess the question is, where does the CO2 go after it's first captured?
This is a question we really need Aaron for, and I'm going to correct you. But yes, please do. But essentially, you're capturing the CO2 and you're removing it, and so the MOF gets used over and over. But you'll probably be able to say that much better than I can. Ken?
So zeolite technology, similar to MOF technology, is for capture only, or for capture. That is what it does. And like lithium hydroxide captures it. The thing is, the zeolites and the metal organic frameworks, you can actually then release the CO2. So what they will generally do is they will put a metal organic framework or a zeolite in a filter. as the atmosphere is passed through the filter, the CO2 is captured. Then they can take the zeolites, put them into a little box and heat them. The CO2 comes out, and as it comes out, it can be pushed into the Sabatier processor and mixed with hydrogen and converted into water and methane. So that's how it works. So it's really a sponge for capture. But the key piece is, as was described by Aaron, metal organic frameworks can capture a lot of CO2 per volume for the size of that metal organic framework. And it's because metal organic frameworks have an immense amount of surface area. So if you consider that it is, let's say, a 1 centimeter cubed piece of metal organic framework, and CO2 can fit into every level of the atomic structure, a 1 centimeter cubed metal organic framework can have approximately 2,000 square feet of surface area to capture CO2 on. So that's the size of a moderate house, if you're thinking of it in that way. So that is how they work and why they are so phenomenal.
Gotcha. Thank you, Ken. So Mickey, I know you answered this question in the chat, but if you want to expand a little bit more, how long does it take on an average from concept to fly the EXPT to the ISS?
Yeah, so it really depending on many factors. Like sometimes the principal investigator might take a long time to develop the idea, or maybe if the concept is complicated, the wait is long. Sometimes, let's say that I think rodent research are very hard to do, and then there's a long queue for that. So the wait could be like 2+ years. But if it's something simple and doesn't require too much complications, like say power requirement, or it has to be pressurized and other stuff, or if the payload itself is small, then the fastest that we've seen is about 10 months.
Cool.
Hey, Julie, I think there was a question, one of the earlier questions was, are we open to direct collaboration? And Mickey and I can answer that on our side, but you may want to answer that on the CSIRO side.
Yes, it just sunk in what the question was, and I responded in chat. But yes, absolutely. I sent a note. Thank you for mentioning that. Please put my email in the chat, and we're always open to partnerships. I'd love to learn more about what you're doing.
And I'll just say from the national labs, the ISS national lab side, although I am a scientist and we do science on station, we don't do it ourselves. We actually help industrial partners and academic partners do their research on station. So yes, we are open to collaboration, and we would love to hear direct collaboration. We'd love to hear what you have. And we're also willing to work with people. For example, you may have some technology that you want to try, but you don't have the whole piece, and someone at CSIRO may have the other piece. We can help bring together different groups to collaborate and do things in space as well.
And
Yeah,
if I may, sorry. Sorry, if I may add, there are many scientists in-house, like Ken and myself have PhD in different areas, and then there are many others too. So, and then we do know the history of what has been done so far in ISS, and then there's actually a NASA database if you are curious what has been done before. But the part of my job that I really enjoy is when I talk to researchers, from academic institutions to Fortune 500 company to startups. I really like learning about what new ideas that they have and how that is applicable to what they do, right? And learning that is very enjoyable because people, think of many different things. I didn't know about moths until I started this job, and how that's applicable to CO2 scrubbing and capturing, and how that, and that has to be utilized more. And there are things that we can learn by managing CO2 in space that is applicable to many problems and issues that we have here on Earth, or product development as well. So I really like that that we were able to come here to share what we have, but wanted to make sure that we are here to have a conversation, and we would like to hear from you all.
Yeah, of course. Thank you, Mickey. Yeah, so to answer your question, bar subs, everyone's open to direct cooperation, so you can find their information and reach out. So we have a question here. It says, how do you address the methane generated in the process? I think this one's for you, Ken.
That is a great question. That I think is the question that has to be answered, because we're good at now capturing CO2, and we're able, through the technology we have, to use that to make water and then go make more oxygen and hydrogen and what have you, or use the water. But what do you do with the methane? So there's a couple of things. First of all, methane is a difficult material to work with from the standpoint of organic chemistry. Industrially, it has to be made very cool to liquefy, so it's more difficult to handle, and it is not very reactive. So people have generated what would be called a post-Sabatier processor, which can take the methane and make other things with it. For example, they can make waxes and oils from it. There are also devices that will, instead of making methane, will make ethylene. So that's 2 carbons, 2 hydrogens, and they're connected by 2 bonds, so a double bond. And that material is much more reactive and industrially is much more useful. And I think that's what you're going to see as these types of technologies develop, will be systems that develop more useful byproducts, essentially, that then end up being starting materials, inputs for other processes. But that's a great question. And right now, if you look at how NASA sees it, they're just taking the methane, they're going to try to cool it and then use it as a fuel, right? That would be the fuel. If you went to Mars, you'd be making your water. The byproduct would be methane production for fuel. But we'll have to get beyond that. And the other thing I'll point out is methane, as gases go, is even worse than carbon dioxide if you're looking at it from the standpoint of a greenhouse gas. So has to be looked at.
All right. That's very good to know. Thank you, Ken. So we have another question, a 2-part question from Barstovs again. So he asked, may I ask which technology do you use to insert MOFs on these rolls? And then the second question is, how many moles/grams of carbon dioxide is enough for 1 gram of MOFs in the roll?
That's going to have to be answered by Aaron.
I was going to say that's what I will pass along and get the answer for you.
All right, Barsov. So definitely reach out to Julie and get in contact with Aaron, and you can find out from there. But great question. So we have another question from Marilyn. She said, are you interested in cultivating microalgae to remove CO2 from the atmosphere? And she has her email there in the chat as well.
Yeah, so in a general sense, absolutely. And if you've got a process that you're interested in sharing, or you want to try an experiment, I would say if you want to try something with us on the ISS National Lab, we'd be interested in hearing about it. There are actually have been a number of attempts at using microalgae or other what we would consider primitive water-based plant life to not only remove CO2 from the atmosphere, but as food stuffs potentially for astronauts. So there's been a lot of thought about that. And at our conference, that is only touched on a little bit, the ISS National Lab conference every year. But I know the ASGSR, which is a conference for microgravity research, they talk about that a lot. There's a lot of ongoing research in that area and a lot of interest. The one last point I would say is, from the NASA standpoint, NASA is hesitant to find solutions that are based on life forms to solve their problems. They would rather have a chemical engineering solution that they can take a wrench and fix it when they're on their way to the moon or Mars than depend upon plants or some such for the survival of astronauts, just because it's harder for them to understand how they would fix it if something went wrong. So just a kind of a sideline, but something to consider.
Awesome. Thank you, Ken. So I just want to remind everybody too that we're going to be launching a poll to gauge how the event went for the attendees. So before everyone drops off, you could fill out that poll, but we're still doing the Q&A. Just wanted to let everybody know. So here's another question. To make CO2 capture and utilization effective, what other materials do we need, and are they readily available?
So, in the presentation I showed, and Aaron kind of also described, you need hydrogen, which, as I mentioned, is difficult to get. You have to bring it with you, essentially, or you have to make it on your way. But other parts of it, like the metal organic frameworks that were described, the catalysts that were described in the Sabatier processor, and the zeolites, those are reusable and are not affected. You can run them many cycles and you're not going to run into trouble. So really it comes down to having access to hydrogen. And that's something that will be considered on into the future. It's always going to be a difficult point. The only other way around that is systems that take CO2 directly to oxygen. So they actually electrolyze CO2 and you just make oxygen and graphite or some carbonous material. But otherwise, I think you're going to be stuck. Hydrogen is going to be a key player.
All right. Another question that we have here. It seems like there's a lot of work in carbon capture, but CO2 utilization has been ignored. Is that true, or what do we say here, you guys?
So I'll just say a little about that. There has been a lot of work on carbon sequestration, and there's still a lot in the popular press, and I think a lot of efforts to look at carbon capture as a solution long term. And the CO2 that is becoming a bigger and bigger problem for us on Earth is the result of us releasing the carbon dioxide out of what has been stored underground in the form of fossil fuels. Really, that's the really big source. Other than things like chemistry associated with cement, concrete production, and what have you. So I can see the logic in trying to take the same carbon dioxide or carbon-containing material and putting it back in the earth, but that process is not an efficient one. That works well over a long period of time when there aren't many people around and you have a huge forest, ongoing forests to continue that process. But I think in our current situation, we have to be better about utilization of materials that are available to us. And I think there's also an economic drive. If you're taking CO2 and you're just pulling it out and disposing of it, that costs a lot of money with very little benefit realistically to the individual. Whereas if you're able to make something and sell it, there's a lot more incentive to actually develop that technology and get it to proliferate. That's my personal feeling on that.
Yeah, I agree with that. And I know that the Aaron mentioned many industries that can take CO2 as a feedstock and do something both useful and profitable with it. So that's the kind of, we want to marry up the technology with the solution. And that's where the partnership comes in when it comes to science lab like CSIRO. We want to get this technology into the hands of people who can commercialize it.
Awesome. Thank you so much, Julie. I guess we don't have any more questions from any of the attendees, but if Mickey, Ken, or Julie have any last questions for each other, feel free. But if you guys don't, thank you everyone for joining. It's been a tremendous event. Appreciate you guys coming out. And Sophia is going to be launching a poll. So if you guys could fill that out right before we wrap this up, that would be tremendous. Thank you again, and I hope everyone has a really nice day. Once again, thank you, Mickey and Julie and Ken, for joining us. You guys were amazing, and it's always been a pleasure having you guys enjoying collaboration for events. So thank you, guys.
Thank you for having us.
Thank you, Salva and Sophia. I was going to say that I am a local. I'm in San Jose, and Julie is in San Mateo. Am I correct?
I'm in, yes.
Right. So that like it's COVID time, but once the doors open, we are happy to meet in person, or of course, exchange emails before then. So, and then of course, if it get technical, we could reach out to Aaron or Ken for more discussion, deeper discussion. So thanks again, everybody, for coming, and thanks Plug and Play for hosting.
Yeah.
Great.
Thank you, Mickey. Yeah, I'll definitely take you up and come visit you guys, because I definitely want to see what's going on over there.
Yes, great, wonderful, and maybe more webinar to come, because this is our second one doing together, right?
Yeah.
Yes. Yeah. So looking forward to more conversation. Thank you.
Definitely.
Cool.
Julie, I had a question for you. It's about the organization and what you guys do. It really does seem to be a industry solution focused organization, right? I mean, it's.
I'd say that's very true. So CSIRO is more than 100 years old. We have 5,500 scientists working in many, many business units. We have solutions in land and water, ag and food. We're working on plastics, oceans and atmosphere, water treatment, energy, data, manufacturing. So there's really a tremendous amount of globally relevant research coming out. And it's very interesting to be in California, because many of the challenges that we're facing environmentally certainly are shared between Australia and California, like drought and wildfire. And so we are actually very excited about the ways in which we can join forces to, no one of us is going to solve any of this by ourselves. So the global partnerships are incredibly important and useful. And so, for instance, in Data 61, we're marrying satellite data with in situ sensors, for example, in inland waterways to predict, algae blooms, things like that. And it's incredibly useful to have these global partnerships where we can exchange data. We've got partnerships with national labs in the US. And for example, the National Alliance for Water Innovation, CSIRO is a member of that. That's a DOE initiative. So yeah, we're all about partnerships, and we're all about commercialization, because we feel very strongly that the research should not stay in the lab. We don't want to be a research push. We want to be a market pull.
And I'm very excited how CSIRO has a strong partnership with Australian space agencies, and as such that, say, for example, you sign a Artemis Accord with NASA, and becoming more and more strong international partner in building the future of economy, where space is a more integral part of it. And with such a tremendous talent and technology and knowledge in Australia, I think it only makes sense for everybody to come together and collaborate and move forward for our future. Yeah, I'm excited about
Amen.
that. Yeah.
That's right.
All right.
All right, it looks like our poll is launched and everything, so I'm going to go ahead and close out this event. Thank you so much, everyone.
Bye, everybody.
Thank you.
Everyone, thank you for the opportunity.
Have a good
Bye.
day.